the process of using analytical technique to find relationship, discover pattern and solve problem with geographic data. The goal of every analysis is to turn data into information. Most analysis involve using your data as input, executing one or more operations, and then visualizing the output data on a map. Geometric analysis is a client-side calculation performed on two or more geometries. Feature analysis is a server-side process performed on one or more feature layers. 3D visual analysis is a client-side analysis of terrain and object. There are 5 terms used in GIS, which are vector analysis, raster analysis, point in polygon, line in area, and area on area. Vector data analysis uses the geometric object of point, line, and polygon. Point is describe the location. Line is described for the river or road. And polygon is described for areas.
So, the next terms that use in GIS spatial analysis is the raster analysis. So, what is the raster analysis? Raster analysis is the process of analyzing spatial information contained in grid datasets. Each cell in a grid contains a value or class which could be related to size, land cover, elevation, or another type of data. By using raster analysis, we can understand data about a place by looking at the pixel that each contains information about a particular geographic elevation. In raster analysis, there is 2 types of raster data that we show in the diagram, which is the continuous data and also discrete data. So, what is the continuous data? Continuous raster data refers to the data that has a quantitative value, for instance, temperature, population, or imagery is continuous data. Discrete data refers to the data that is quantitative and has values that are mutually exclusive. For example, it could be the presence or absence of a species or land cover. In raster analysis, choosing the scale is one of the most important part because it depends on your project. Because in the diagram that show in the slide, the high resolution, which is at the left, the smaller grid size is the more computing power and storage your raster analysis and data required. And for low resolution, the larger grid size is smaller in file size, but if your grid size is too large, then you will lose detail in your raster data. We move on to the example of raster analysis. For a situation, a hydrologist may use this type of analysis to calculate the slope and runoff in an area. Alternatively, an ecologist may use it to develop a habitat sustainability model. A geologist may use raster data and analysis to create a soil map that shows the type of soil found in an area and how they are distributed. So, in conclusion, raster analysis is helpful for projects that involve mapping and visualizing large value of data in the environment and geospatial research. Furthermore, we also have the terms in GIS which called point in polygon. Point in polygon is a spatial operation in which points from one feature dataset are overlaid on the polygons of another to determine which polygons are contained within polygons. So, in the point in polygon, we have the raycasting algorithm. The raycasting algorithm is one simple way of finding whether the point is inside or outside the simple polygon. Is to test how many times a ray starting from the point intersects the edge of the polygons. If the point in question is not on the boundary of the polygon, the number of intersections is an even number if the point is outside, and it is odd if it's inside. This algorithm is sometimes also known as the forcing number algorithm or the even part algorithm. The algorithm is based on a simple observation that if a point moves along a ring from infinity to the probe point, and if it crosses the boundary of a polygon, possibly several times, then it ultimately goes This observation may mathematically prove based on the Jordan curve theorem. The next algorithm is called winding number. Another algorithm is to compute the given points within winding number with respect to the polygon. If the winding number is non-zero, the point lies inside the polygon. One way to compute the winding number is to sum up the angle subtended by each side of the polygon. However, this involves costly inverse trigonometric functions, which generally makes these algorithms slower than the recasting algorithm. Luckily, these inverse trigonometric functions do not need to compute. Since the result, the sum of all angles can add up to 0 or 2 multiples of pi, only it is sufficient to track through which quadrants the polygon's winds, as it turns around the test point, which makes the winding number algorithm comparable in speed to counting the boundary crossings. For simple polygons, such as the Lagrange, both algorithms will always give the same results for all points. However, for complex polygons, the algorithms may give different results for points in the regions where the polygons intersect itself. Well, the polygon does not have a clearly defined inside and outside. In this case, the former algorithm is called the even-odd theorem.
Line in area. A line is a feature in geographic features, GIS. This depicts linear geometries such as a road, river, and highway. Lines are one of the most fundamental vector data types used to describe geographic data. In contrast, an area is a polygonal structure. On the Earth's surface, there's a denotes a closed or the bounded region, such as a park, lake, or administration border. Example to use line in area. Situation: road segment within municipal zone. Problem: traffic congestion is a growing issue in the city, and there are the complaint about condition of road in different municipal zones. Some zones seem to have more road-related problems than others, and there are the need to identify specific areas for targeted improvement resource allocation. This step for the problem solving. First, data analysis. Use GIS software to evaluate the road segment. These the boundaries of municipal zone. Number 2. Problem identification. Analyze the finding to discover every traffic zone and areas with a high concentration of road-related concern. Number 3. Resource allocation. Consider road condition, traffic volume, and the strategic relevance of road. Number 4. Community involvement. Seek input from residents and stakeholders to ensure the proposed solution align with the community needs and concern. Number 5. Implementation. Work with the Department of Transportation to implement the recommended improvement and maintenance strategies in the identified zone. Also, monitor and evaluate the impact of changing order. Area on area. The terms area on area refer to geometric connection in Geographic Information System (GIS) in the spatial analysis when one polygonal geographic feature is located with the spatial limits of another polygonal